Last lesson ended with a warning. The cost model we built, count the steps, charge 1 unit each, quietly assumes that touching any piece of memory costs the same. This lesson breaks that assumption, and I want to break it with a demonstration. Here are 2 functions. Both sum the same grid of numbers, 4,000 rows, 4,000 columns, about 17 million integers. The first walks the grid row by row. Finish a row, move down. The second walks it column by column. Finish a column, move right. Same grid, same 17 million additions, same number of steps in our model. The only difference is the order we visit the cells. Now race them. The row version finishes in a few milliseconds. The column version? About 10 times slower. Same big O, same work on paper, 10x apart on the stopwatch. Nothing in Lesson 1 explains that. Something underneath the model is deciding the price of each step, and this lesson is about meeting it. Let's narrow down where the time goes. Each pass through either loop does 2 things. It loads 1 integer from memory, and it adds that integer to a running total. The additions are identical in both versions. Same operation, same count. So the adds are innocent. All that's left is the load. Now, a load asks memory for a few bytes at a specific address, so look at the addresses each version asks for. The grid lives in memory as one long block, row after row. So the row version asks for address 0, then 4, then 8, immediate neighbors, marching left to right through memory. The column version asks for address 0, then 16 kilobytes later, then 16 kilobytes after that. Because stepping down 1 row means stepping over 4,000 integers. Same number of loads, completely different pattern of addresses. And that pattern is the only variable left. So the conclusion forces itself on us. What a memory access costs must depend on where you reach and on what you touched just before. The model said 1 step is 1 step. The machine disagrees. So how much can a single load cost? Here's the uncomfortable arithmetic. A modern core runs at several billion cycles per second, and an integer addition takes about 1 cycle, a fraction of a nanosecond. A trip to main memory, the actual RAM, takes around 100 nanoseconds. Do the division. In the time 1 value crawls back from RAM, the core could have done a few hundred additions. And this gap is not an accident of 1 chip. It grew. For decades, processor speed improved at a sprint, while memory latency improved at a stroll, and the difference compounded, year after year, until architects gave it a name: the memory wall. The consequence is blunt. On modern hardware, arithmetic is close to free. The real cost of a program is moving data to the core. A processor that went to RAM for every single value would spend over 99% of its life doing nothing. Waiting. The hardware's answer to the wall is to cheat with copies. Between the core and main memory sit layers of progressively smaller, progressively faster storage called caches. Level 1, L1. Tiny, tens of kilobytes per core, but about 1 nanosecond away. Level 2, bigger, around a megabyte, roughly 4 nanoseconds. Level 3, shared between all the cores, tens of megabytes, 10 to 40 nanoseconds. And then, main memory, gigabytes of it, 100 nanoseconds out. Every load checks L1 first. If the value is there, that's a hit. Pay a nanosecond, keep moving. If not, a miss, and the request falls down a level, then another, paying more at every floor until something answers. Notice what this whole tower is. It's a bet, and it's the same bet at every level. Whatever you touched recently, you are about to touch again. Modern performance rests almost entirely on that bet coming true. Nanoseconds are hard to feel, so let's slow the clock down. Pretend 1 nanosecond is 1 second. An L1 hit is now 1 second. Grabbing a pen off your desk. L2, 4 seconds. Opening a drawer. L3, half a minute. Walking to a shelf across the room. Main memory, a minute and a half. Down the hall to the storage closet. And it keeps going. A read from a fast SSD on this clock is over a day. Asking another machine on the same network, most of a week. Now replay our column loop on this clock. Every load that misses all the way to RAM is a hallway trip, and the column version takes that trip 17 million times. The additions, the part we so carefully counted last lesson, are the 1 second at the desk. That is what locality means, physically. It's the difference between working at your desk and commuting down the hall for every single word you read. One mechanism explains almost everything else, so here it is. When a load misses and memory sends data up, it does not send the 4 bytes you ask for. It sends a fixed size block called a cache line. On most machines, 64 bytes. Ask for one integer, receive 16. Your integer, plus its 15 nearest neighbors, parked in L1. Why ship blocks? Because the expensive part of the trip is the trip itself, not the cargo. Once you've paid 100 nanoseconds to reach RAM, hauling 64 bytes back costs barely more than hauling 4, so the machine hauls the whole neighborhood. And notice what the hardware is silently assuming, that if you wanted this byte, you'll want the ones next to it, 64 bytes at a time. That one design decision is about to crack our mystery wide open. The bet the hardware keeps making has a name. 2 names, actually, and they're the 2 most useful words in performance work. Temporal, locality. What you touched recently, you'll touch again soon. That's why caches keep your recent values. Loop counters, running totals, hot variables, they live in L1 and cost basically nothing. Spatial locality. Near what you touched is what you'll touch next. That's why a miss hauls in the full 64-byte line, neighbors included. Real programs honor both bets most of the time. Not because programmers are careful, because code is loops and data is sequences. Every structure in this course is fast when it keeps these 2 promises, and slow when it breaks them, which is finally enough machinery to go back and solve the race from the top of the lesson. Replay the row version, but watch the cache lines this time. The loop asks for cell 0, miss. 100 nanosecond trip hauls back the line, 16 integers. Cells 1 through 15, already here. 15 hits, 1 nanosecond each. Cell 16 misses, hauls the next line, 15 more hits. One slow trip buys 16 cells. Average cost per element, about 7 nanoseconds. Now the column version. Cell 0, miss. Step down 1 row, 16 kilobytes away, different line. Miss again. Every single access lands on a fresh cache line, so nearly every access pays the full trip. And here's the brutal part. Each miss hauled up 16 integers, and the loop used 1. The neighbors would be useful when the traversal wraps around to the next column, but by then, 4,000 other lines have shoved through the cache, and this one is long gone. Evicted. Same 17 million loads. The row version pays the trip once per 16. The column version pays it nearly every time and throws away 94% of everything it hauls. That is the 10x. Not the algorithm, the order. Sequential access has one more gift waiting. The CPU watches the addresses you load, and when it spots a pattern, this line, the next line, the next, it stops waiting for you. It starts fetching lines you haven't asked for yet, ahead of the loop, so by the time you arrive, the data is already in cache. This is the hardware prefetcher. On a steady forward march through memory, it hides the trip almost entirely. The array stops being read 1 line at a time and starts streaming, limited only by raw memory bandwidth. Tens of gigabytes per second on a laptop. And that is the full answer to this lesson's title. Arrays are fast because they're contiguous, one solid block. So a scan is sequential. So every line hauled is fully used, and the prefetcher can see the future. The array isn't lucky. It is, by construction, the exact access pattern the machine was built to reward. Now meet the opposite. A linked list stores each element in its own separately allocated node, and each node holds a pointer, the address of the next one. The nodes can be anywhere in memory, and in a program that's been running a while, they are. Watch the same sum on a list. Load the first node. Miss, 100 nanoseconds. Where's the next node? No idea, until that load finishes. The address of step 2 is data, sitting at the end of step 1. The CPU can't start the next fetch early. The prefetcher sees no pattern, because there is none. And every line hauled up carries 64 bytes the node barely uses. The neighbors belong to other objects entirely. So the traversal becomes a chain of dependent misses. 100 nanoseconds times 17 million, that's nearly 2 full seconds, where the array took milliseconds. Both order in. Both visit each element once. One streams, one commutes. Now, lists do have real wins. Cheap insertion in the middle, no resize spikes, and Lesson 5 is exactly about when those wins are worth it. But walk in knowing the toll. Once you see this, you see it everywhere in production. Analytics databases like ClickHouse store tables by column, not by row, precisely so a query that scans one field becomes one giant sequential read. That's our row race, one on purpose. It's how a single machine scans billions of values per second. Game engines moved from objects scattered across the heap to tightly packed arrays of components, because simulating 10,000 entities every frame is a loop, and loops love contiguous. The default sequence type in every mainstream language, a C++ vector, a Go slice, a JavaScript array, a Python list, contiguous block, not linked nodes. The defaults encode this lesson. And remember the oddity from last lesson? That real sorting libraries switch to insertion sort, a quadratic algorithm below a few dozen elements? Now you can name the reason. At that size, the whole array is 2 or 3 cache lines. Insertion sort just slides neighbors around inside L1, and its steps are so physically cheap that the fancy algorithm can't pay off its overhead before the work is already done. So does any of this dethrone Big O? No. And it's worth being precise about why. The hierarchy changes the price of a step by a factor of 10, sometimes 100. It does not change how the number of steps grows. A quadratic algorithm with perfect locality still loses to a linear one at some n, always. 100x is a constant, and the gap between n and n squared is not. The growth ladder from Lesson 1 is undefeated. What the hierarchy explains is everything Big O leaves blank. Why 2 order n functions differ by 10x. Why fewer, friendlier steps beats fewer steps at real sizes. Why the structures that run production are arrays under the hood far more often than the textbooks suggest. So from here on, this course prices everything twice. First, the shape. How does cost grow? Then the layout. Is each step a desk reach or a hallway commute? Get the shape wrong and no layout saves you. Get the layout wrong and you leave a factor of 10 on the table. You now know why the contiguous block of memory is the hardware's favorite shape. Next lesson, we take that block and build on it. Because the array you actually use day to day, the one that grows, a Python list, a Go slice, a JavaScript array, is a careful machine wrapped around a fixed block. We're going to build one from scratch. Allocation, growth. The doubling trick from Lesson 1's amortized math, and the exact moment an innocent-looking append quietly costs order n. See you there.